So good morning, everyone. Welcome to today's Debye lunch lecture, which will be given by Thomas van Swieten from the Condensed Matter and Interfaces group. And Thomas will talk about, nanoscale thermometry using optical methods, and specific about the photonic artifacts in them. So Thomas, the floor is yours. I will be recording the lecture, and if people online have questions, then they can ask them in the chat, and I will then pose them to Thomas. Yes, Alphonse. Nobody, or at least very few people. The reason why it's at 11 is that it was otherwise impossible to find a lecture room at the Uithof today at 12. So it is, hands are tied in that regard. Okay, Thomas, floor is yours.
Yes, thank you. Thank you, Imar. I would like to talk with you about some of the work of my PhD, which is focused on mapping temperatures with high spatial resolutions. And we use luminescent materials for that. But before going into the details of this technique, I would first like to discuss some of the already existing temperature mapping techniques with you. So one of them that's already quite popular is infrared thermography, which uses the black body radiation of a material as a measure for temperature. And you already have, or we already have, commercially available systems such as this one, which can map the temperature on several different systems, such as this. I think it's a computer chip or something like that. And the scale bar is here a few millimeters. So it also already gives you an idea of the spatial resolution that you can achieve here. A different technique uses atomic force microscopy, and in this technique, the AFM tip scans over the substrate, and the substrate has a different electrical conductance on each location, and that depends on the temperature. And this you can also use as a measure for temperature. But both techniques and all other techniques also have their limitations. Such as limitation of this technique is that it uses infrared light and far infrared light, and therefore the spatial resolution is generally not so good. Spatial resolution in this case is quite good, but here the range of systems that you can apply it to is rather limited. You can imagine. So Robin Geitenbeek, the person who worked on this project before me, already developed several luminescent materials, and one of them is this sodium yttrium fluoride host lattice doped with erbium and ytterbium. And he synthesized, in this case, microcrystals. And the erbium ions in these crystals show this thermally or temperature-dependent emission from the 2H11 half and the 4S3 half levels, which are in thermal equilibrium already at room temperature. And this results in this trend in the luminescence intensity ratio that we can understand via Boltzmann's relation. And he studied together with Ilse Ravenhorst these micro heaters made by a company called Dense Solutions. He deposited the microcrystals on these heaters and saw that the set temperature deviated quite a bit from. So this is the set temperature, and this is the temperature that he measured in the different regions of the heater, and he measured quite some different temperatures. So already interesting. He achieved spatial resolutions of about 10 micrometers. So really interesting. But we tried to do that a bit better, and we used nanocrystals, also sodium yttrium fluoride with erbium and ytterbium. Due to the smaller size of these crystals, we can hopefully achieve higher spatial resolutions. And we also used upconversion excitation, which basically takes place via this ytterbium ions, which you can excite with infrared light, and then multiple ytterbium ions in their excited state transfer the excited state energy to erbium to populate these thermally coupled excited states. And then again, you get this temperature-dependent luminescence. And if we integrate the emission bands and take the ratio, take the logarithm of the ratio and plot that as a function of the reciprocal temperature, we can see that it nicely follows this Boltzmann behavior, which we can later on as a means to convert the ratio back to a temperature, so as a calibration basically. But when applying this technique to microscopic systems, or to basically using this technique in a microscope, requires to focus the excitation laser, and focusing the laser leads to high intensities. So we're first interested in seeing if it doesn't affect the luminescence, and we see that it basically does. So at higher excitation intensities, we see that the spectrum changes, and we can understand this via not a 2-photon upconversion process, but via a 3-photon upconversion process, which populates this 2H9 half level. And emission from this 2H9 half level not only goes to the ground state, but also to the state above the ground state. And this exactly matches the 555 nanometers that we observe in the spectrum. Fortunately, we can correct for this by recording a reference spectrum, and in this reference spectrum, no 2H9 half emission is present. And if we then subtract the reference spectrum from a spectrum that has this 2H9 half emission, then we can find the shape of this 2H9 half emission, and then subtract this via linear combination fitting from each spectrum that we acquire. Now, Dens developed their systems in the meantime, and they got this newer next generation fancy shaped spiral, and they from the side it looks like this, where you have this silicon substrate as a support, and it is covered by silicon nitride membranes in which the molybdenum spiral is embedded, and this molybdenum is of course a metal. And using their COMSOL simulations, they can model what the temperature distribution should be. Now, if we deposit the nanocrystals on the microheater and map the luminescence with confocal microscopy, we can make such intensity maps of the integrated green emission intensity. And for each pixel, we have a spectrum, and we of course first correct it for this excitation power or excitation intensity effect. And by taking the ratio between these two emission bands, we can convert the intensity map to a temperature map. And we see quite an interesting thing in the temperature map. We see that the spiral is colder than its surroundings. Well, the spiral is basically at room temperature, so it cannot be that the spiral is colder. So there must be some weird kind of artifact going on here. And one of the possible artifacts that can happen is we call it self-interference, where we have the emitter that is basically close to a mirror, and here the mirror is the molybdenum metal, the spiral, and the emission that is directed towards the mirror is reflected and then interferes with the direct emission from the emitter, and this causes self-interference and basically changes the total color of the green emission depending on the emission angle, and that is what you see here. And then if you acquire the luminescence with a numerical objective with a certain NA, you record a specific luminescence spectrum. But if you change the numerical aperture, you can imagine that you also record a different emission spectrum. And one way to test if we are indeed dealing with these photonic artifacts is by recording temperature maps with different numerical apertures. And if we do that and we make a histogram of all the temperatures in the center of the spiral, we indeed see that the distributions are completely different mean values, which indeed indicates that we are dealing with photonic artifacts here. To further prove that this is indeed a photonic artifact, we measure temperature maps at various set temperatures and determine the temperature difference between the pixels on the spiral and not on the spiral. And that is what we plot here. And we observe that it increases with increasing set temperature. And this is exactly what we would expect based on the sensitivity of our thermometer. So another indication that we are indeed dealing with photonic artifacts. And now it's now interesting to see if we can correct for this phenomenon and still use this technique to map temperatures. To do that, we go back to the Boltzmann equation and see what this photonic effect has on the Boltzmann equation, and basically affects this pre-exponential factor. And this pre-exponential factor contains the spontaneous emission rates, and that is effectively changed by collecting different different parts of the radiation pattern of the emission. So by recording maps of the temperature at room temperature and determining what the distortion from or the deviation from C is, we can determine the so-called we call it the photonic distortion factor for each pixel, and we can then use this to correct all the temperature maps at higher temperatures. We see that this procedure works quite well, because if we look at the map at 523 Kelvin, we still see this spiral, and after correction, we don't see this. So can we now also compare it with the experiment and can we compare the experiment with the simulation that they did at the dense solutions? And yeah, we indeed see that the experimental values match quite well with the modeled values. So also a nice indication for dense that their next generation heater indeed is better than the previous one. But we are interested still in this photonic artifact. And to go on with this, we slightly changed the substrate. So first we were dealing with still a rather unknown and inhomogeneous photonic substrate. So we did not know exactly what the thickness of these membranes was. Also the specifics of the molybdenum were not really known. We used a rather thick layer of nanocrystals so that we can make quick temperature maps. We did not need to acquire the luminescence for too long. But this is, so this basically averages all the temperature errors. But we are interested in quantitatively determining how big these errors are. So we asked our colleagues in Zurich to make a substrate like this, where we have a gold reflector, which is of the size of about 1 centimeter by 1 centimeter. And on this gold mirror, a alumina spacer was sputter coated, and the thickness of this spacer is about 600 nanometers. And on top, so this basically increases over this centimeter by 600 nanometers. And on top of the spacer, we spin coated the monolayer of nanocrystals, because the dimensions of the lateral dimensions are rather large. We can assume that at the location of the emitter, the distance to the mirror is basically constant, and in this way have a very controlled photonic environment, and also don't have issues with the averaging of the errors, and can really study the errors as is. So we use two different thermometers for this. Again, the erbium-based thermometer with the characteristic temperature-dependent emission from the thermally coupled levels. And we also prepared a different thermometer. This one is based on holmium, and holmium has an emission spectrum like this, where you see a weak blue emission, also a green emission and a red emission from the 5F5 level. The green emission was from 5S2. And what the temperature-dependent mechanism is of this thermometer is basically that from the 5F3 level, you have temperature-dependent multiphonal relaxation, which feeds the green emitting level. So at higher temperatures, the excited state population of the green emitting level increases, and also the green emission increases. That is what we also see here in the spectrum at higher temperatures compared to the spectrum at lower temperatures. Now, how does this emission spectrum look on our substrate when we acquire it from nanoparticles that are deposited on our substrate? And we see for a distance to the mirror of 310 nanometer, that the spectrum looks like this. And at a so still considerable 2H11 emission, but at 450 nanometer distance, we see that the 2H11 emission is much weaker, and we again can explain this via the different parts of the radiation pattern that are collected by our microscopy objective. And if we go specifically into the radiation patterns of the at these emitter mirror distances, we can see that in both cases, so for 450 and 310, most of the emission is not within the collection angles of our objective. So those are the yellow parts. But if we zoom in, then we can see that still considerable part of the 2H11 emission is within the collection angles for this 310 nanometer geometry, which is not really the case if we compare it to the zoom in at 450 nanometers. And this indeed follows also the experiment. So here we see that we cannot collect too much of the emission, and we see that the emission intensity is weak. And here we see the opposite. To understand how this now behaves as a function of the emitter mirror distance, we calculate the radiation patterns at all the wavelengths within the integration ranges of the green emission, and determine in that way by summing what emissions we by integrating the emissions that we collect, we determine the collected emission, and we see these oscillations as a function of the emitter mirror distance due to the self-interference effects. And if we plot this on the longer distance scale, we see that the oscillations dampen. So this indicates that these photonic issues are mainly a problem when you are doing, when your nanothermometer is in a microscopic environment or is in an inhomogeneous photonic environment on the microscopic scale. What we see here is also that the phase for the two emissions is slightly different. So we see that this peak is a slightly different emitter mirror distance than this peak. So this translates also into oscillations in the intensity ratio. And we see that the calculated trend nicely follows the experimental ratios that we obtained by measuring spectra at all different emitter mirror separations. Now, well, we can of course imagine that if we translate the ratios then to temperatures, that we also see these oscillations in the temperature, and we see that for the measurements at room temperature in blue, that the oscillations have an amplitude of maximum amplitude of about 50 Kelvin, but this becomes even higher to 100 Kelvin at set temperatures of 373 Kelvin. So what we did here is that we attached our substrate to a heater to physically increase the temperature of the heater, and we then see that the apparent temperature that we extract from the luminescence measurements increases. And this is the same as we saw before with the microheater. There we also saw that the temperature deviation increased with increasing temperature, and that was due to the relative sensitivity, so how sensitively the thermometer responds to temperature. We can do the same experiment for the holmium-based thermometer, and well, the difference between the holmium and erbium-based thermometers was mainly the difference in emission energy. That's the most important difference. The emission energy in erbium was about 20 nanometers, and here it is even more than 120 nanometers. So how does this affect the radiation patterns of the two different emissions? We see that in the case of 400 nanometer distance, we still collect considerable green emission, but the red emission is not collected so well. These radiation patterns are normalized, by the way. For 450, we see that the radiation pattern completely changes, and you even see this double lobe. And we see that we barely collect any green emission. This, of course, leads to much larger distortions of the intensity ratio. This is a logarithmic scale, and this again then translates to much larger readout errors of the temperature. And we see that at some temperatures, even the readout, it is not possible to determine the temperature because the ratio was beyond the calibration of this thermometer. So to compare, when we have small emitter, when we have small differences in emission energy, we see already quite large temperature errors. But when we increase the difference in emission energy, these temperature errors become really huge. So this is not only the case for this basically well-controlled geometry where we have a mirror with a high reflectivity and an emitter with two emission wavelength or two different emission energies. To further investigate this and also how this translates into other systems with different reflectivities, we consider this as more simple geometry where we have a mirror with permittivity epsilon 2, and we have a medium of epsilon with permittivity epsilon 1 in which the emitter resides, and it has a certain separation from the mirror and emits emission in all directions, and we can calculate this. And if we then determine the maximum readout temperature, so basically the maximum readout temperature of these oscillations, we find an expression as this one, where we have the relative sensitivity, so how sensitively the thermometer responds to temperature, but also this important one, this difference in emission energies divided by the average emission energy. So this explains why we saw the larger temperature errors for holmium. If the difference in emission energies is much larger while the average emission energy is rather constant, then we observe larger errors. This also has important implications for instance, infrared thermometers, which are popular in biologic systems, where people really need the high penetration depths of the infrared thermometer. There, in those cases, this value is rather small, which thus intrinsically leads to larger temperature errors. So that is something that people should be aware of when applying such thermometers. It also depends on the reflectivity, and it depends on the range of collection angles that you collect with your microscopy objective. So for low NA objectives, this guide becomes really large, and you also then have large temperature errors. So this gives also an idea on the experimental parameters that you need to tune to minimize these errors. If we then consider a few geometries, we first consider here the geometry of a perfect reflector with the emitter in alumina. We see that the maximum temperature error behaves as these two. We see that it nicely corresponds with the experimental values. Then we also consider the slightly different geometry, glass water, where the emitter is in water and the reflectivity is much lower. But still we see that the temperature errors can be quite high. So this are the thin dashed lines. And we see that the temperature errors can be between 1 and 5 Kelvin at room temperature. And this doesn't seem as too big of an issue, but these thermometers or these systems, this is probably comparable to most biological systems. This means that if you are in a biological system and using these thermometers, then you can already get temperature errors of 1 to 5 Kelvin, which can basically mean the difference between a living and a dead cell. So important to consider. We did a similar kind of derivation for an emitter that is on the surface of a plasmonic particle, plasmonic particle in this case. And we see that the temperature errors behave like this. So not so much as in the extreme case of a perfect reflector, but still considerable. So I discussed with you some of the errors today, but how can we deal with these errors, except for the correction that I showed on the microheater, which is possible in dynamic systems or in static systems, but in dynamic systems, you cannot correct in this way. So you need maybe first to minimize the readout errors by controlling all these parameters. So by choosing the emission energies of your thermometer, but also by using microscopy objectives with high numerical apertures. Reflectivity is something that you maybe cannot always choose. That is something that is maybe more specific to your sample. But an alternative approach could be to also correct for these distortions via the local field information of your emitter. And this is inspired by the work of Lin that was published in Nature Communications 5 years ago. And what they basically did was they recorded Raman spectra of different geometries and saw that the after subtraction of a fluorescent background, that the relative intensities were quite different for different geometries. Well, this should not be the case. So what they did is that they used the distorted background spectrum together with a reference spectrum as a probe for the local environment of the thermometer, and then use this to correct the Raman spectrum and get back the right relative intensities of the peaks. We could do a similar thing with our thermometers by incorporating, maybe, I not tried it, but definitely interesting, I think, to incorporate a broadband emitter into the thermometer and use the broadband emission as a probe for the local field information, and in a similar way correct your luminescence after recording it. So to conclude, we showed that it is possible to use luminescence nanothermometry to map temperatures with high spatial resolutions. But we saw that photonic artifacts in high excitation intensities can affect the readout temperature. And these photonic artifacts especially can really lead to huge readout errors of more than 400 Kelvin. And this is something that people should take into account. To conclude, I would like to thank first, of course, Sander for the nice collaboration, Freddy and Andries for supervision, Dave for his help with the experiments and with the microheater experiments, and the people from DENS and the people from ICC for their help and supervision. And thank you for your attention.